Okay, good morning. My name is Jeff Catlin from Edgecore Networks. So today I'm going to go over two contributions that we're doing here at the European Summit to the Telco group. So we'll get started on that. So we have two contributions we're doing. Have to hold this, yeah? Yeah. Okay. One is a cell site gateway router, and we'll go over that at a high level. And the second one is what I just called an aggregation router, for lack of a better term. So we have two different products we'll go over, and then maybe some time for some Q&A, depending if we're on schedule. So just before we dive into the products here, who is Edgecore? And you've seen on some of Paul's slides previously listed as Acton. So Acton is a company that's been around 35 years. It's an ODM company that produces networking equipment. Edgecore is a wholly owned subsidiary of Acton, and Edgecore is simply the go-to-market brand for the technology that Acton produces. So you may see in some of these presentations those two names used interchangeably. At a high level, that's the difference. Acton is the parent company, Edgecore is the go-to-market brand. Okay? So first question is, why open cell site gateways, right? So why are we doing this contribution, and what does this mean for the carriers that need these products? So quite simply, it's the updates to the existing equipment that's needed as the mobile backhaul and the cellular usage is surging. So not only just 5G that's on the horizon, but for 4G today too as well. There's just massive installations that are going on, massive usage by consumers, and this is forcing upgrades to the infrastructure. So a natural choice for open networking principles is at the edge of the network. And that's because there's very large numbers of units being deployed of something. So that is a great opportunity to take advantage of the open networking principles. So some of those principles that can take advantage of in this type of product are listed here. So they're very simply, the removal of single vendor lock-in. Traditional incumbents produce equipment today. It's very costly, and they have very slow technology roadmaps. So today, if you want to get a feature or a function on a incumbent roadmap, you meet with your sales rep and you state your case, and 6 months, maybe 12 months later, your feature appears, and you move along at the snail's pace of that. Truly open hardware in an open networking environment can run different software options. So you can start with one NOS on top of your hardware, and if that's not sufficient, you can wipe that off and go to a totally different NOS. So much different than a traditional hardware model where you buy the prepackaged software on top of the hardware, and that's all you can run from then on until the end of time. With open hardware, of course, you can choose either commercial packages or open source packages and change them at will. With the open networking type of ecosystem, there's new operating systems that allow you to run arbitrary agents in alongside the NOS. So things that expose additional value, maybe VNFs or something like that. So that's always a possibility. And a very simple thing that's sometimes overlooked is the removal of the vendor lock-in on simply the pluggable optics. So traditional network suppliers, lock their optics and their pluggables down, and they force you to buy those pluggables from them at a very inflated price. So in an open networking model, you're able to buy anyone's optics and cables and plug them into the devices and have them work. So those are the few reasons for why open cell site gateways. So at a high level, what are the requirements for an open cell site gateway? Well, it's got to be outside plant compatible with temperatures. These will normally go in cabinets at the base of a cellular tower, so they have to be rated from minus 40 to plus 65 degrees, so very harsh temperature environments. 19-inch rack mountable. They got to be very small units, so 300 millimeter maximum depth to fit in these cabinets. Of course, they have to have redundant power supplies and fans, those standard types of things. They have to support clock synchronization techniques such as IEEE 1588 and synchronous Ethernet. support local timing inputs and outputs to go along with the clock synchronization techniques, and ability to support long-haul optics for backhaul that may be more than 20 kilometers away to the next hop up the chain. So a very simple picture of where a cell site gateway, would fit would be here in this type of drawing. This drawing I lifted from a previous presentation AT&T did back in Texas. That shows the very simple topology of where cell site gateways, are needed. So this is our product today that we're contributing. It's we have it in the booth downstairs. You can go see it. This product conforms to a specification that AT&T will go over later today that they're putting forward for cell site gateway routers. This one is 24 ports total for links that would connect to cellular equipment. 16 of those ports are standard 10 gig SFP plus ports. 8 of those ports are SFP28 ports, so they can run at 25 gig. So some of the cellular equipment that's coming out either now or in the near future is 25 gig capable. So this gateway router here has the client or the downlink ports that are 10 gig and 25 gig capable. Okay, and it has, of course, a couple of 100 gig standard QSFP28 for uplinks. This is a deep buffer switch architecture. It's based on Broadcom silicon. So if you're familiar with the Broadcom family, this is based on their Strata DNX silicon. So it's really geared towards carrier environment. It's high quality of service, deep buffer type switch architecture in the silicon. And again, this supports your standard AC and or DC power supply options. Power supplies from the front, minimal things accessible from the rear, which are just the fans. Here's a view of the front, and if you guys just want to kind of look at the numbers, I'll read off what they are. So of course, number one is the 2 power supplies. Number 2 are the 200 gig backhaul ports. Number 3 are the 16 10 gig SFP plus ports. Number 4 is a USB storage port located on the front. 5 and 6 are 1 pulse per second input and output ports. 7 and 8 are 10 megahertz input and output ports for timing synchronization. Number 9 is an input for a GPS antenna. Number 10 is a micro USB port, and that's used for serial console type access. 11 is a time of day port for timing needs as well. Number 12 is a standard RJ45 console port, so 2 console ports on this device. 13 represents the 8 SFP ports that are capable of 25 gig or 10 gig. So these are the ports that can do either 10 or 25 gig. Number 14 is a bits port, again for timing needs. 15 is the standard Ethernet 1 gig triple speed management port. So a lot of activity there in the front panel of this type of device. In the presentation, I put the cursory block diagram for those who care to look at it. I guess one of the key takeaways here is it's a very busy design that we have here in front of us. So again, it's a 1RU 300 millimeter type of design. A lot of different pieces of components and circuitry that go in to make up this design, not only with the switching, but also all the timing synchronization aspects of this design. So what is included in a design contribution? So a design contribution that we normally do at Edgecore is when we go for OCP accepted status on a product. And to be an accepted product, you submit not only your design specification, but all of your design files. So the intent of the open source submittal of the design files is someone could either take your design and reproduce it as is, or take your design, make changes to it, and bring those changes to market. So we support either of those. We do it under a permissive license that allows users to take the design and do with it what they will. And with that design package comes all the things that are listed here. So it's the paper specification, a programming guide, all the schematics that are required in the hardware design, the Gerber files, the board files out of the native design tool are included, all the mechanical files and the step files to recreate all the mechanical packaging of this is included. Any CPLD code needed that goes in, or FPGA code on this design, that's contributed in source format and binary format, and a complete test plan of how to test the product if one was to reproduce it. So a very comprehensive design package is contributed along with the specification for our contributions. So a schedule of what this looks like is the specification is complete, and that's ready for review today. So that should be on the wiki. If it's not, it will be on the wiki today, available for you guys to download. The complete list of design files that I just went over, all those are ready and uploaded to the OCP servers, and those are ready for review. I'll be going over this design contribution at an incubation committee meeting, which are public, and you guys are welcome to join, on October 11th. And then after the incubation committee meeting, and we go over that, it's out for review for a short period of time, and then a voting process. So if all goes well, we would expect this design to be accepted, hopefully, in early November timeframe. So about a month away or so is our hopes on this design. The schedule for the product itself, again, we have samples available today. We've distributed samples to software partners so they can start porting their software. We expect field trials and POC tests to start running as soon as that software is available within Q4 and run throughout the remainder of Q4 this year. And we expect volume GA, either late Q4 this year or early Q1 next year, depending on how those field trials go. So that's the first product contribution. That's geared towards cell site connectivity needs. I can pause here and take any questions for this contribution before we get on to the next contribution.
One question is are the 10 gig interfaces also useful as 1 gig interfaces? SP+?
Yes, so the question was, are the 10 gig SFP interfaces capable of utilizing 1 gig SFPs? And the answer is yes, they are available for 1 gig connectivity, which is most prevalent today for a lot of the equipment. Right. Okay, I'll move on to the next one, and we can always come back at the end and do other questions. So the next contribution we're doing is for aggregation router. Okay, so where would an aggregation router sit in a very generic picture in a topology? So it would sit upstream from these cell site gateways or something that is connecting at the access layer. You would need something to aggregate these new devices that are being deployed. Again, why would we do open aggregation routers, and why would these be important to carriers? Well, it's much the same principles as with the cell site gateway. So as new cell site gateways are being deployed because of bandwidth requirements going forward, that forces pressure on the aggregation network that's upstream. So again, the benefits of open aggregation routers that sit one step up in the topology are much the same as they are, of course, for the cell site routers. You remove the vendor lock-in and the slow roadmaps. You have hardware that can run many combinations of network operating systems depending on the features and functionality you want. And again, the pluggables that go into these devices. An aggregation router starts to have a lot more optical interfaces that may be 100 gig or 400 gig in the future. Very expensive optics, and you don't want to be locked into buying those optics from a single source. Again, high-level requirements for an aggregation router, 19-inch rack mountable. These may not be in cabinets, but they still need to be kind of NEBS compliant, but probably will not be outside plant type of temperature requirement. I don't foresee these being in a cabinet. But again, support for the standard redundant power and fans, support for clock synchronization techniques are needed in these as well. High-density 100 gig connections are definitely a requirement. The ability in the future or variations of the base product to support 400 gig in the future is definitely needed. Deep buffering designs and large TCAM capacity. Those are two things that are needed in these aggregation routers. And again, ability to support long-haul optical modules. So at Summit here today, we're contributing our specification for two products and a family of products that we'll be doing over time for aggregation. We have two products that we're showing here today, and we're showing these downstairs in our booth. So we have a 40-port 100 gig switch and an 80-port 100 gig switch. And again, these are based on Broadcom silicon. So these are based off the same family, Strata DNX, but these are based off a chipset called a Jericho 2. So if you're familiar with the Jericho and Jericho 2 types of products, these are very, again, high quality of service, expandable TCAM on here. So we have, in these designs, we have included the TCAM expansion chip in here that allows you to go to many millions of routes in your route table capacity in these hardware designs. It's a very deep buffer switch offering many gigabytes of packet buffer, not megabytes, as is included in standard like data center switches. IEEE 1588 and Sync-E support on these devices. At the top of the slide here is listed the commercial software partners that we've lined up initially to support these platforms. And those four are listed here. There'll be more, obviously, but these are the initial four. Below these pictures here is the list of open source software components that we provide for these types of platforms as well. And that's everything from Open Network Linux to Sonic and the Chord type software suite from ONF. So kind of a look at the building block designs that we've done for these products. We kind of come at this in a way where let's take these components and try to do the designs that have the most components up front, and then do variations by depopulating components going forward. So this here is a depiction of that 80-port design. That's the 3RU design. So on the left side here of your screen, you have what the main board would look like. And that would have, the Jericho 2 switching silicon, that TCAM expansion chip, which is called the OP2 from Broadcom. And you'd have gearboxes in front of that piece of switching silicon. And those gearboxes would convert the 50 gig PAM4 SerDes that are native on that Jericho 2 chip into standard 100 gig NRZ interfaces, 25 gig NRZ interfaces. So those gearbox allow you to get the maximum standard 100 gig port density off of this Jericho 2 type of device. Right, so that's the baseboard that has a connector on it where we plug in one of our CPU modules that we offer with all of our other open compute designs. And then there's a board-to-board connector on the back of that, and on the right side here represents what the mezzanine board would look like to get that 80-port design. So 40 ports on the baseboard. The mezzanine card is almost identical to the baseboard. And plugs in through this board-to-board connector. And now between those two boards, you have 80 ports of 100 gig. Now the Jericho 2 chip here being a 400 gig capable chip by default, so it has 50 gig SerDes on it. You can envision that making mixture of 100 gig and 400 gig ports would be by removing these gearboxes on either both or one of these PCB assemblies. So if you remove the gearboxes on the top PCB, and just routed those SerDes interfaces out to standard QSFP DD connectors, you'd have a mixture of 40 ports of 100 gig and let's say 10 ports of 400 gig. Right? You could remove the gearboxes on the bottom mezzanine, the bottom main card, and have a total 400 gig solution of 20 ports of 400 gig in a solution that's all geared towards aggregation devices. So again, we're coming at this from a building block design, and we're coming at this a little different in that We're not contributing our design per se right now. We're contributing the specification, and what we'd like to get is some feedback from the community on the specification and what different variants may be required of this platform going forward. So a view of the schedule for this contribution. So the spec, the initial spec I did is available today and should be on the wiki today if it's not already there. So we'll make that public, and we'll hopefully get some feedback on that spec from the community of different variations or different things that the community may want to see in these aggregation type routers. So after a review period, we'll move forward, and then we'll submit the design package for this platform as well. We're targeting the end of Q4 to submit our design package based on feedback, of course. The schedule for this product, samples, early samples are available now. So we have a prototype downstairs of this platform. We've distributed those early platforms throughout the month of October here to software partners that will begin porting their software to these designs. We expect, field trials and POC tests to be throughout Q1 of 2019, and volume GA of this product maybe late Q1, early Q2. So this is kind of early on in the silicon life cycle from Broadcom. So these are early products in that regard. So it's a good opportunity, to get some response here from the community. So again, we're doing this a little different where we're putting this specification out early enough to hopefully get some feedback. So I feel there's plenty of innovation left here to do in this family of products. Again, you could easily see how you could make a mixture of 100 gig and 400 gig ports in one of these designs. You could make a complete 400 gig aggregation router. By a mezzanine card, you could make coherent optical ports available on a mezzanine card for long haul, backhaul situations. So again, there's plenty of innovation to do here, and hopefully we'll get some feedback from the community on this. So to follow up and to finish up here, I urge consumers of products to purchase and go out and look at the OCP marketplace, not for these products per se, but for any open products that you can buy right through the marketplace through the OCP website. So I've listed the URL here. Download these specifications and give them a review. So I've put the URL for the wiki here. So the specifications are public information. You guys can download them, and please provide feedback through the wiki, or you can provide feedback through the mail list, rather. Or I put my email at the beginning of this presentation. If you're not comfortable providing feedback through the email list, you can provide it directly to my personal email address. Again, there's a telco call, our monthly call, which is Thursday of this week, 7 p.m. this time. So I urge you guys to all join that if you're available. That's the opportunity for you guys to see perhaps some more in-depth information on these things we've talked about today, and ask questions and become more involved in the community. So that is all I have. I can certainly take some Q&A for a few minutes if we have time.
Anyone have questions?
We just one.
Please.
One of the things that I mentioned regarding my design was the lack of choice for silicon. You mentioned again this one silicon provider. As far as I understand, there should at least be a little more choice for the Ethernet switching side. How do you see things about alternate chip providers?
Yeah, so when you get into cell site aggregation routers and aggregation routers one step up, you're right, the choices in silicon are limited. I will say that the Broadcom, I'm not a Broadcom employee, but the Broadcom DNX silicon is a good choice. They have a lot of the feature set that's required for products in those places in the network. It would be good, I agree, to see other silicon choices as well, but I don't see a lot out there right now today to do some of that, especially in the aggregation router section, to do those speeds and capacity, to do something that's FPGA based or something like that, just doesn't, to me, lend itself to fit into a good cost structure yet. So I agree. The silicon, I think choices are limited right now for these types of devices.
You said for this type of speeds, you consider that any speed below what you just showed, 80 times 100G, or the cell-side gateway was well, quite a number of high-capacity ports. So this is the only requirement for now is such high-capacity devices, or may there be room for a little bit lower speed, lower cost, lower power in particular?
There is a lower capacity and I guess cost envelope cell site gateway that is defined through another open source community called TIP. So there is a TIP meeting in a couple weeks in London, and I think you'll see more announcements around that. So there is a cell site gateway defined there that has lower port counts, and some of the ports are lower speed capacity, but the requirements from that group were the route table sizes and capacities that were required in that specification. Again, lends itself very nicely into that DNX family of silicon. So,
okay, thanks for this. But curious question: why do we have TIP and OCP so separated? That doesn't seem very good.
that's a fair question. I don't run, either of the groups. I'm just a participant. But
Yeah, so the
Maybe you can pull them together, like, just go across the channel and.
so TIP has a different licensing model than the OCP. So that's one of the differences, and then there's other kind of a delineation between IT gear versus telco gear, and our group kind of somewhat sits in that middle area, which it may be really clear for the data center folks why there's a TIP and an OCP, and we kind of run the middle and we understand or think both worlds. But there is a slight difference in the licensing model between TIP and OCP that differentiate the two. So. Well, I have to refer you to the TIP folks to explain their model, but there's a way for the participants to maintain some intellectual property over some algorithms and stuff having to do with some of the typically modulation techniques, that kinds of thing that they feel very important. And TIP was, agreed, and in order to move forward, created a new licensing model for that. They're still kind of the same, but Facebook was involved in the creation of both of them. There's a lot of similarities, but, yeah. Okay.
all right, thank you.